In this video, we're going to be talking about a simple application of taking the ARIMA models and running those models in R. Now, we know that a non-seasonal ARIMA process can be written in this form, where you have an AR component, you have a differenced time series with a degree of differencing equal to D on YT, and then you have an MA component. Okay, so what we need to do is to select appropriate orders for the AR component, for the MA component, and the differencing component. So there is a process for doing that. What we want to do is we want to use the KPSS test and look at whether there are unit roots in the data first, and whether we need to difference the data and how many times we need to difference it, and whether we need to even do seasonal differencing. So here D refers to the regular differencing that we do, whether, when we take the differences between one observation and the next. And capital D here represents the seasonal differences that are required to make the data stationary. And the seasonal differences are the changes between one year to the next, okay? And so the KPSS tests give us some indication of what these two Ds can be. And so once we know the degree of differencing, whether the regular differencing or the seasonal differencing, then we can try to select the order for the AR component and the MA component by minimizing the AICC. And typically we use a stepwise search. The algorithm that is there in R would use a stepwise search to figure out which model has the lowest AICC. Now we already know the formula for AICC. The idea here is the automatic function called ARIMA works in the following way. So what it does is it selects a current model with the smallest AICC from these different models that are out there. Okay, so you have an ARIMA 2D2, ARIMA 0D0, and so on and so forth. In step 2, R is considering variations of the current model by increasing or decreasing P from the current model. And so P and Q would both vary from the current model by just plus or minus 1. So stepwise, you're increasing or decreasing the lag structure of your ARIMA model, and excluding a constant, and then trying to measure what is the AICC. Once you find a model with the lowest AICC, that becomes the current model, and the iteration continues. Okay, so we keep repeating step 2 until we cannot find a model with a lower AICC. Let's take a look at a web usage, and this data is displaying some kind of a trend in recent years, but we can try to look at its PACF and ACF structure. So you can do this by the gd_ts display command. Again, a very useful command to plot the ACF and the PACF data together. If you want the PACF data to appear here, you need to put this extra argument here which says plot_type equals partial, and plot this. So you have your data here, and you have your ACF represented here, which is decaying, as you can see, in a sine wave manner over time. And then you can see that there is a PACF structure here shown, where the autocorrelations, at least 2 and almost 3, this third spike is close to that Bartlett band. So if we really wanted to guess what type of model would we start with, this would be an AR2 or an AR3 process. What we could do is we could also mutate this data and take a look at the differenced time series. So here we are looking at the difference in the value of the web usage, which again is showing a sine wave pattern. This time it's showing you 2 clear partial autocorrelations that are significant. Okay, but for the sake of it, we can take a look at 3. So here we have we are fitting an ARIMA model on our data by saying PDQ. PDQ is, when you are thinking about the non-seasonal ARIMA model, this is what you would use. It is going to be lowercase. And the first component is saying that the AR component should be 3. We should difference the time series once, and we should not have any MA components. And then we report the fit of the data. Of course, we have different types of information criterion that are given to us here. Okay. And you have the different parameters that are associated with the different components represented here. So when you fit a model like this, you don't need to difference it again. You can literally just say 1, and this would difference the data automatically. Okay, but you need to know that you need to difference the data. So maybe you can look at a KPSS test on the data and see whether you need to difference it or not. Okay, so choosing your own model, how do you go about that? If you are using the ARIMA model and you have figured out that you definitely need to difference the data, but you don't really want to guess what the AR and MA component is, you can just rely on the ARIMA automatic command, and you can just impose that the data be differenced once and to make it stationary, and then you can report the data. So here what R is finding is that the best model is going to be not what we had earlier, 310, but instead a 111 model. Okay, this helps us because we estimate less number of parameters, and we have our model which says that the data was differenced once. So you have one AR component, one MA component, which is reported here. The parameters are reported here, and then you have the information criteria. And you can try this at home. When you try with different ARIMA models, you will not be able to find a model which is going to beat an ARIMA 111. This is what should happen if the algorithm is running correctly for ARIMA models. Now, one thing to note is that this is a quick and dirty way of using ARIMA and using the automatic algorithm. If you want R to search through a larger set of models in the data, then you can add these two arguments called stepwise equals false and approximation equals false, and then report. So what it does is it then reports a model which is 310, and the AICC is 512. In the earlier case, it was 514. So notice that the AICC is lower in this case, okay? And we also know that when we had put 310 here, it was 512. So this was not a guess, this was actually me cheating because this was run before that, okay? So you have a lower AICC, and so this is the model with the best fit when you have looked at a larger set of models in the search. What you can do after this is once you fit a model, this was fit, okay? So we had fit 310, ARIMA 310 was our model. We can take a look at our residuals and some diagnostics with residuals. So the residuals look like this. This is a plot of our residuals over time, and the autocorrelation function of the residuals is displayed here, which is nice because it does not show you that there is any type of autocorrelation or serial correlation present in the residuals. You want this to happen. You don't want these autocorrelations to be crossing the Bartlett bands. That would mean that you haven't exploited some patterns that were already existing in the data. Okay, so and then there's a histogram of the residuals that is plotted here as well. But you can do a sophisticated test on this, which is a portmanteau test, a box Pierce or a Loom box test for the model. So in this case, what you find is the Loom box value, the p-value is 0.7, which is a high p-value. Anything over 5 or 10% would indicate that the residuals are white noise, which is what you also see in this type of an autocorrelation function, okay, which is a great thing for us. If we have a model that we've estimated and the residuals are white noise, that means we have exploited the patterns that existed in the data for forecasting purposes. Now, how good the model would perform is a different story altogether, but for now, the residuals are white noise. So that's a good thing. Okay, and then you can use this model to forecast 10 periods ahead. Okay, so this is a forecast, and you can see that there are these 80 to 95% confidence bands that are presented. Now, just to kind of summarize this one more time, if you are modeling using the ARIMA function, you want to first plot the data and identify any unusual observations to make sure you know what is going on with the data. If necessary, you want to transform the data using a Box-Cox transformation to stabilize its variance, for example, using power functions or using logs. If the data still look non-stationary after you've taken logs or power functions, you might want to take the first differences of the data until the data are stationary. Okay, this is for non-seasonal models. You want to take a look at the autocorrelation functions in the next step and the partial autocorrelation functions and try to think about or come up with AR models or MA models that seem appropriate. So the number of lags for each of these components that you see fit. Once you have those, you will try your chosen models. I'm assuming there would be many, maybe 6 to 10 models, and use the AICC criteria to search for a better model. So every time you estimate a model, you want to note down what is the AICC and then find a model that beats another model with a lower AICC. Okay. Finally, once you found the model that has the lowest AICC, you want to check the residuals from your model by plotting the autocorrelation function of the residuals and also doing a sophisticated portmanteau test like a box-Pierce or a Leeuwenbach test for the residuals. If they do not if they do not look like a white noise, you may want to try a different modified model, increasing the number of lags and so on and so forth for the ARMA components. And once the residuals look like white noise, you can go ahead with your forecasting exercise. So this is, when you're doing things semi-manually. The automatic modeling procedure with ARIMA is going to skip some of those things that you have to do manually. What you can do is plot the data, identify the unusual observations, and stabilize the variance. Now, ARIMA would automatically select a model. It would do all of that you were doing manually, but in the algorithm, this is all programmed. So ultimately, you want to check the residuals from your chosen model once you've used the ARIMA function by plotting the autocorrelation function of the residuals and doing a portmanteau test of the residuals. Again, if they don't look like white noise, I doubt that they would not look like white noise when you're using this algorithm. You would then try a different modified model. Okay, so once you have your residuals or white noise, you're good to go and you can actually forecast. So just to reiterate this in a flowchart, once you plot the data, you identify unusual observation and understand the patterns. The next step is basically stabilizing the variance. Usually you can take logs. You can go two ways. You can select the model yourself or you can use an automated algorithm. I would say do both, okay, to understand what is going on. Once you want to select the model on your own, you want to difference the data until it appears stationary and use a KPSS test or an ADF test to make sure that the data are in fact stationary. Then you want to plot the autocorrelation function and the partial autocorrelation function of the differenced data to try to determine the possible candidate models. And then try your chosen models to find the models with the lowest AICC. Then do the residual diagnostic tests, plot the residuals, do a portmanteau test, and make sure that the residuals are white noise. Okay, if the residuals are not white noise, you want to go back to this ACF and PSCF and try different models. Okay, finally, you want to calculate forecasts. But if you were using the automated algorithm, ARIMA would find the best ARIMA model for your time series, and then you can do the residual diagnostics and calculate your forecasts. So here you can take a look at an example on your own. which for some parts of this code you might want to refer to chapter 3. It's not necessary to do this right now, but the idea here is to, once you get to some kind of uh, using your GG underscore TS display, once you're looking at an ACF and a PACF, here for example you see 3 spikes for this data set, you want to then say that yes, the PACF is suggestive of an AR3 model. So the candidate is going to be 310 if you were differencing it once, okay, and no other obvious candidate. So you want to fit some models that are close to the 310 models and see what you get, okay. And in this model, we are actually just restricting ourselves to the non-seasonal ARIMA models, okay, by saying PDQ is 000, which is the seasonal component. Okay, so there's no seasonal component here, and we are imposing the structure here for the model. And then we can take a look at the residuals in the next step and see if they are actually white noise. They look white noise, but we still can do a portmanteau test. The p-value is 0.24, which is greater than 0.1, so the residuals are white noise, so we're good to go. And then you can then forecast your time series. You can even try a GG underscore ARMA fit, which is a little more advanced, and the book talks about it a little bit. So you can take a look at what happens. So here you forecasted. If you had a test set, you can actually then see with different accuracy metrics, so how well your forecast performed. Okay, finally, you can forecast. I'm not going to go into the details about how we write the models theoretically, but the idea is to have the prediction intervals always presented with your forecasts. The prediction intervals always increase in size with the forecast horizon. So the further you want to forecast in the future, the prediction intervals would keep rising. So if you want to forecast 10 periods, 10 years ahead, those prediction intervals would actually look a lot larger than if you were just forecasting 2 years ahead, for example. So prediction intervals can be difficult to calculate by hand, but R does that for you. The calculations assume that residuals are uncorrelated and normally distributed over time. And prediction intervals from ARIMA models tend to be too narrow. This is because the uncertainty in the parameter estimates is not accounted for, and also that ARIMA models assume that historical patterns will not change during the forecast period, which they can. So this is a sort of a downside. And the ARIMA models also assume that the future errors are uncorrelated. Okay, so you can practice this at home. You can take the United States GDP data or GDP data for any other country from global underscore economy and find a suitable box clocks transformation for the data, find a suitable ARIMA model that fits the data, and do the residual diagnostics, and then produce forecasts from the model, especially in this time. With COVID-19, you want to forecast the US GDP or GDP of another country that you are interested in.